For centuries, humans have measured time using motion. Pendulums swinging back and forth, gears turning inside mechanical clocks, and quartz crystals vibrating within modern watches. These systems are precise, but they are not perfect. Over time, their components wear down, and even the most advanced clocks can drift, losing seconds over the course of a year. That might seem insignificant, but when you're guiding satellites, powering global financial systems, or synchronizing data across the entire planet, even a single second can change everything. In the search for a truly stable and universal way to measure time, scientists turn to something far more reliable: the atom. Atoms possess a natural rhythm, a constant vibration that never changes, no matter where they are in the universe. An atom on Earth and an atom billions of light years away tick at exactly the same frequency. This makes atoms the most dependable timekeepers nature has ever offered. Traditional atomic clocks typically rely on cesium atoms, which have an extremely consistent internal frequency. Inside these clocks, a beam of atoms is exposed to microwaves, similar to the ones used in everyday kitchen appliances. These microwaves supply energy to the atoms, causing them to shift between energy states. This transition only happens when the microwave frequency perfectly matches the atom's natural frequency. When that alignment occurs, the system is said to be locked. By counting these microwave cycles, we can define the length of a second with incredible accuracy. Without atomic clocks, modern life as we know it simply wouldn't function. They keep GPS systems accurate down to centimeters and ensure global networks, financial, communication, and digital, remain perfectly synchronized. Even the timestamp on your phone depends on their precision. Today's most advanced atomic clocks are so precise that they wouldn't lose a single second over the entire lifetime of the universe. But scientists are still pushing the boundaries of accuracy. In our research, we use an element called Ytterbium, which offers an even more stable internal frequency than cesium. More importantly, Ytterbium ticks nearly 60,000 times faster. That higher frequency allows us to measure time with far greater precision. The principle remains similar, but instead of microwaves, we use lasers. Currently, these optical atomic clocks are large, filling entire rooms. But efforts are underway to make them smaller, more robust, and even portable. These next-generation clocks could revolutionize navigation systems, allowing us to track fast-moving objects, like rockets in space, with unprecedented accuracy. Their sensitivity is extraordinary. They may one day detect subtle shifts in space-time itself, help predict earthquakes, or even uncover entirely new forces of nature. A clock that can keep perfect time for billions of years is more than just a scientific achievement. It is a tool that can transform our understanding of the universe, from safeguarding global systems to unlocking the deepest mysteries of physics. The pursuit of perfect time is, in many ways, a journey to better understand reality itself.